Hi, let's talk a little bit about this energy skate park. So, before we were doing the energy skate park and we used our skater like this, and we went ahead and put them into the skate park, into the half pipe here. And you can see that they start with a certain amount of kinetic energy. Let's slow her down and or sorry, potential energy, and it converts to kinetic and then back to potential and then back to kinetic as you go down the ramp. And now you guys can say, okay, we know mgh is potential energy, so at the highest point we should have the most potential energy, and that 1/2 times mv squared is kinetic energy, and so at the bottom, when you're traveling the fastest, you should have the most kinetic energy. Right now, you and I know that this is a situation that is considered ideal conditions where there's no such thing as friction. Right, so what if we introduce friction? If we introduce friction, then energy can be both kinetic and potential, but it can also become thermal energy because friction, the surface's rubbing, is going to not create, but transform energy from this pie chart, from this bar graph, into thermal energy. So let's add a little bit of friction and see what happens. So a little bit of friction means that every time that the skater is moving, the system of the skater and the skateboard is actually not losing, but transferring some of its energy. You see, I have to keep checking myself because I'm using these words incorrectly. It's transferring some of its energy from either potential or kinetic into thermal energy. So over time, the pie is taken over by thermal energy, or the bar graph is dominated by thermal energy. And eventually, all of the energy in the system, remember the system being the person riding the skateboard, right, is going to become thermal energy. And that's going to cause our skater to stop. So this is really what happens in real life. Now, it's going to happen a lot faster in real life, like this. And then your skater is going to end up slowing down to a stop, right? Eventually over a long period of time. It's kind of annoying. Okay, there we go. All right, sweet. So our skater is eventually going to stop here once all the energy is in fact thermal energy. Now let's talk about what happens here. So this is something that I was bringing up a lot when you guys are doing your work on the skate park here, is when the energy becomes thermal energy, it doesn't just stay. Like, the skateboard doesn't light on fire because it's so hot. The person's not sweating profusely. I mean, she's just been riding a skateboard, right? So what happens to that thermal energy? So a lot of times that friction that generates that thermal energy through conduction is passing that energy into the ramp or into the air, okay, around it. So energy is considered to be leaving the system. Okay, so this is where we are going to switch screens. So hold 1 second for me. Okay, so here we have our skater, right? And I cut her out so that we could look at this more carefully. And normally, when we consider a system, here we go. Okay, our system is our, this is not visible. Let's use something that's more visible. This is our system, is the skater on the skateboard, right? And we draw this invisible barrier around her. So we're considering her to be the system, and everything else is the surroundings. Okay, now we are making this mental barrier around our skater and saying, okay, the system is what contains the energy that we had, right? So that means that this pie graph is the pie graph of the energy that was in the system, right? But what happens is, once we have heat energy that is generated, right, a lot of that heat energy ends up leaving the system and going into the surroundings. Why? Because thermal energy, right? When we have friction, we're rubbing our wheels onto the surfaces. That's generating, it's passing some of the energy from the skater into the wheels and then down onto the track, onto the ramp. So we're going to have some heat generated there, and that heat is going to end up through conduction moving away from our system into our surroundings. And eventually, what's going to happen is, actually, this pie is going to be gone, right? The entire pie of energy is gone because our skater no longer has any energy, right? So our skater now has no energy at all, right? There's no energy in the system at all, right? And that's because energy has all left the system. Okay, so why does this matter, right? You're probably thinking that. Like, who cares? We talked about this. I thought it was over. Let's look at a situation where we have a ball on a track. So let's say there's a ball at the top of a hill, okay? And the hill is some height. H equals, okay, that worked. See how I changed colors and didn't work? H equals 10 meters, okay? And then at the bottom of the hill, there is a box. Here comes the box. There we go. There's our box. And we want to know, okay, some things about this. First thing we want to know is, and this can be like a real world problem, okay? So I don't know why you'd want to be pushing a ball down a hill and having it hit a box, but maybe we want to know some information about the box, okay? So perhaps we want to know how much force or how much energy is available to do work on the box, right? So if we want to answer that question, we need to remember that mechanical energy is equal to our GPE plus our KE. And you guys need to remember, okay, also that we don't have any kinetic energy if the ball is not moving, right? So I'll just write that right here, V equals 0. So that means kinetic energy equals 0. So that means we just need to calculate our GPE. Now, let me tell you the mass of the ball. It's 7. Oh my goodness, come on. 7 kilograms is the mass. You know what? We're just going to write it over here. It's 7 kilograms. There we go. Now we know the M, we know the H, so we can find the GPE, right? GPE is equal to 7 kilograms. And remember, we know what sorry, I should have written the equation. Let's write that. M times G times H, right? So that means it's equal to 7 kilograms times 9.8 meters per second squared, which remember, this is a constant, times H, which is 10 meters, which is 70 times 9.8. So let me use my handy dandy calculator, TI-83, right here. And we'll say, okay, it's 686 joules of energy, right? So that's how many joules of energy are in our system. So not only is it our GPE, but it's also our mechanical energy. It's the total energy available, right? Now, what if I told you that when the ball rolls down the hill, there's friction? And you're going to be like, wow, this is the first time we're actually doing something that's real. There's friction during this portion, right? There's friction. Now, let's say that friction takes 102 joules, right? So what that means is 102 joules of energy are going to be removed from the system when the ball rolls down the ramp. So we now need to think about, okay, how much energy is left to do work here is going to be our total energy, 686 joules, minus our frictional subtraction, 102 joules, right? And that's going to end up with 584 joules of energy can do work on the box. So that's how much energy is going to be able to do work on the box, right? So now let's say that we've got that much work, okay? So we've got this energy to do work. So the energy that can do work is 584 joules. There we go. And remember that work is equal to F times D, right? Okay. So there's 584 joules of energy available to do work. There's another question we can ask, which would be something like, okay, how far, let's see, right? Hello? What just happened? I'm really sorry about that. I don't know what just happened. We can say something like, okay, how far can the box move with 10 newtons of rightward force from the ball? Okay, well, now we know W equals FD, right? So our work is equal to 10 newtons times D. So solve for D, and it's just 584 divided by 10, which is 58.4 meters is the distance. So a 7 kilogram ball on top of a 10-meter hill will roll down the hill and push this box 58.4 meters. Pretty wild, right? Now, I made up how much friction is removed, but you can actually find this value here in a different class that's not mine. For now, I'll just tell you how much is removed or whatever. So now this adds another wrinkle to the original puzzle of using conservation of energy. Now we're thinking about how it applies to both thermal energy and systems and work.